This is a section on diffraction. We have to sketch the variation with the angle of diffraction of the relative intensity of light diffracted at a single slit. So what we have here is, this is a barrier, this is another barrier, there's a gap or an aperture there. The waves come in from this direction and they go through and they curve round. This is the diffraction effect. However, what you have to draw is something a bit more sophisticated than this, because in the gap this is basically a source for new waves to start from any point across here. When the waves go from there or to there, they will interfere with each other. Now this wave going that direction, this wave in that going that direction, they have a phase difference of 0. It's exactly in phase. So this central fringe, the central band, is very pronounced and is very clear. Then you have a point here where the wave coming from this side has gone, let's say, 10 wavelengths. This has travelled 10.5 wavelengths. So we have destructive interference. Then here again we get some more constructive interference. So you basically, the diffraction pattern is, if we look at it from the bottom, is that there's a big central part here which is very clear, very constructive, and very pronounced. Then we have an area of destructive interference. Then we've got a very weak point of constructive interference, and we're going to look at why that is now. You can go to this web page here, which is a good one. Now you know what happens here. What will the pattern look like afterwards? So pause and try to draw what you think it would look like afterwards. These are the solutions. Okay, this is a screenshot of the Faustad Java. These are the plane waves coming in here, the wavefronts here. This is the aperture. The central band is very clear. Then we have some destructive interference, because obviously the waves from different parts of this are interfering destructively. Then we have some constructive interference, but this is much, much weaker than the central band, and we'll look at that now. Here's another way of looking at it. When you have this is the gap, this is the aperture. When the wave comes in here, each point along the gap can be considered to be a source of a new wave. Each one is a source of a new wave. Then these waves travel in one direction, and if it's constructive interference, then you will get a bright fringe. If it's destructive interference, you'll get a dark fringe. Of course, the central fringe is going to be the brightest by far, and then it's going to be have a destructive interference on either side, and then a very faint constructive interference afterwards. And this is what it would look like. If you have a light going through a gap, you get the main central fringe has been very bright. The light is spreading in all directions, but you don't see the light here because it's interfering destructively with other light that is coming through the gap. Here, the light is interfering constructively with other light which is going through the gap. We have the angular half width. Between here and here is the angular width. So we're interested in going from there to there. This is the relationship that we're looking for. And we'll find out that this bright central fringe is going to be this angle here is going to be lambda divided by b. Lambda is a wavelength, b is the size of the gap, the aperture. So we have to derive this formula that the angle is equal to lambda divided by b for the position of the first minimum. So this is the first minimum, and this would be lambda divided by b as an angle from there. This would be 2 lambda from b, and this is basically called the angular half width. This is the size of the gap, which is b. The light comes from the top, and from the bottom go in this direction. Now, are they going to interfere constructively or destructively? Well, it depends on the angle. It depends on the size of lambda. Now, you could argue that this has travelled one wavelength greater than the wavelength from there, and that's true. However, so that could be constructive interference, but it will not be constructive interference because there's also a wave that's coming from the middle of the beam as well, and this is going to be half a wavelength out of phase with this one here. The one slightly below it will be half a wavelength out of phase with the one there. The one near the bottom will be half a wavelength out of phase with the one almost in the middle. So for every point you get along here, if this is lambda, for every point you come across here, there's another part of the slit which will allow, which will be the source of a wave, which will be in antiphase with it, which will interfere destructively with it. So this will always be first a minimum, because this is the point of destructive interference. So this angle here, the sine of that angle is equal to lambda divided by b, using basic trigonometry. So the first diffraction minimum, why is this a minimum and not a maximum? Of course, this interferes constructively with this one, but destructively with the ones in the middle, basically. Consider the point in the middle of the slit as being a point source in the direction theta, in that direction. It has a lambda divided by 2 path difference from the top of the point source at the top of the slit down to there, and we get destructive interference. So this is the point. For every point along the slit, there's another which emits a wave which is going to have a lambda divided by 2 path difference or phase difference. So that will always be destructive interference. Yeah, this angular half width, this is that angular width of the central fringe, the central beam. The half width is lambda divided by b, as we've just proved. And you see this corresponds to the first minimum. This next fringe is going to be there. This next minimum is there. Next fringe is there. But it gets much, much fainter. The central fringe is much brighter than the others. This is going to be lambda over b. This is going to be 2 lambda over b. This is going to be 3 lambda over b. These are always going to be the dark fringes where we have destructive interference. Now we have some questions. This is one diffraction pattern. Notice the central fringe here. This will be lambda over b. This is the next fringe. This is 2 lambda over b. What has happened here? Well, either the angle has got smaller, which means either lambda has got smaller or b has got larger. Here we have another picture here. So these crosses here correspond to the minima between the fringes. This is another diffraction pattern, not from one hole, from many.